presentation where my topic was to investigate the plausibility of an FFT system for concentrating solar power. So you might be asking, what is an FFT system apart from the pictures that are already given here? So first up, I'll introduce myself. I'm Shaun Combrinck. I was born in the year 2000. I'm currently a final year at UP and I'm doing my bachelor's for engineering mechanical. So before we discuss the FFT, we need to take a step back to the background, where a concentrating solar power system can be defined as a harnessing solar power system for harnessing useful work. This can take forms such as in power generation, for HVAC, specifically heating in this case, for industrial purposes such as for smelting, or even domestic use such as for hot water generation. And one of the most applicable ways of doing CSP is with a solar dish, where it concentrates solar energy to a single point, as is demonstrated in the figure to the right. And generally, it is seen that parabolic shapes are the best efficient designs for this. But the precise parabolic shapes for CSP are complex and expensive to create. An approach to this can be using a faceted membrane parabolic dish design, which simplifies this in that it uses a vacuum to focus the membranes, and ultimately leading to reduced parabolic component costs. However, the reflective membranes and glue deteriorates over time, and as such require yearly refurbishment for experiments, and this is not ideal. For instance, some of the previous years during their experiments, even during the experiments, these membranes could be seen to start delaminating. So in the same way, initially my project was also to investigate melting of metal using such a system. However, when I went to inspect it, I found the dishes would require refurbishment and all my budget would go into this. And this is considered non-conductive to progress. This led to an attempt to address these problems, where I asked, can a system of comparable quality be created, such as this one, but with a more durable concentrating mechanism? And with that, that led to the conception of the FFT system as demonstrated to the right. And this then led to the question, is it plausible? With this in mind, this presentation will cover the concept of an FFT system, followed by the experimental model that was created after it. This was then used for experimentation and observations. Along with this, a theoretical model was also constructed and then correlated to the experimental results. Some considerations of the research project are then given, followed by the conclusion and some recommendations. So, for the concept of an FFT system, we can start out by the attempted simplification, where the parabolic reflector shape was taken and simplified to a flat reflector shape. To concentrate the energy then, Fresnel lenses were added, but this then provides two possible problems. One, the Fresnel lenses overlapping each other, and the second one is the Fresnel lenses obstructing the incoming solar radiation. And for this reason, the system configuration was taken and completely overhauled, where the receiver was moved down and the focusing facets reoriented towards this receiver. And thus we have our final concept, a faceted Fresnel lens dish, or FFT system for short, where we've gone from a single point focusing system to a multiple points circular focusing CSP system, where it is currently a hybrid between the current types of systems in the industry, specifically linear Fresnel lens systems and single point focusing dishes. Based on this concept, an experimental model was then constructed, the first of its kind termed FlexD1, standing for Fresnel lens experimental dish number 1. This then consisted of the main structure, subdivided into the main dish structure and the main supporting structure, joined together by a tilting mechanism. On the main dish structure, you then find Fresnel frames and mirror frames joined together on the guide rail. In the center of this main dish structure, you then find the receiver, which consists of a conduction core placed inside a receiver container or bucket with a solar alignment structure constructed above it to focus it with the sun. This was then filled with an insulating perlite cement, but this could also be replaced with a non-cement based insulating method in the future. This is just for this project. So with this FlexD1, 4 primary experiments were then done, and some of those pictures are given below. In the top left one, you can specifically see the system oriented towards the sun. Experiment 1 was then the first operational experiment of FlexD1, and it was considered a failure This is because the winds caused the mirrors to shake around, leading to shaking solar focus points and ultimately to input losses as well as to the melting of a receiver bucket, as shown in the figures below. This then further led to increased heat losses, and ultimately all of this led to low temperatures and an insignificant performance. Along with this, during this experiment, the suspicion of thermal contact resistance inside the receiver also came up. And to the right can be seen an interesting observation that was made. And during this experiment, at one instance, a cloud covered the sun, and below can be seen the accuracy of these focusing facets, as it almost perfectly pictured this over onto the receiver. And this was just found very interesting. Experiment 2 was then considered to actually yield useful results, where the receiver melting points were first repaired using the insulating perlite cement, while also using duct tape as a temporary solution for stability against the wind. This experiment then consisted of two parts or sections. Part 1, which used air, and Part 2, which used water as a target materials. During the transition from Part 1 to 2, a phenomenon that was termed the quench process was observed, and as the name suggests, this occurs when the cold water was poured into the already hot receiver core, subsequently quenching it before a steady state temperature would be reached between the two. This led to the suspicion of thermal contact resistance inside it being increased even further. After experiment 2, all the mirrors were covered, and subsequently leading to experiment 3, which was a solar cutoff. As the name suggests, there was now no solar input going into the system, and as such it would only experience a thermal decay or heat losses. From this, it was observed that the system had a slow thermal decay with an average heat loss rate of 5.3 watts. This then led to the question of, if it has such low losses, why is it underperforming? This could then point to either a problem with the input solar power or input losses, or the already suspected thermal contact resistance inside the receiver. These questions then led to experiment 4 being done. Experiment 4 was then the thermal decay testing of the receiver, and this was repeated 2 times. The first time the system was still cold or not warmed up, and as such saw an abnormal heat loss rate not matching with experiment 3. However, the second time it was now warmed up and saw a much more reasonable heat loss rate matching with experiment 3. During this, the quench process was again observed, and this led to this being the third time seeing it, and as such not being a fluke but rather an inherent part of the receiver. From this then, the existence of the thermal contact resistance in the receiver was confirmed. Along with this, a theoretical model of the system was constructed, and this was done by first setting up a mathematical model, but it should be considered that this system has a unique receiver design, and as such, correlations had to be used where not all of them match the system perfectly, and some assumptions had to be made. This model was then implemented in Excel because it allows for easy tracking of data values during its implementation to see bugs and fix them early on, while also providing easy visualization for post-processing purposes. This theoretical model was then correlated to the experimental results, of which the final product can be seen in the top right. For easier identification, some of the regions were also color-coded to see how they compare. From this, it could be seen that the outside of the receiver, by the end caps where there are more unknowns such as winds blowing over the receiver, that there are discrepancies, and this is likely due to the unknowns and accumulated errors within the theoretical model, but also possibly in the experimental sampling rate. But at the core of a receiver, where the target material is and our primary focus, it is seen that the system did appear to correlate well, specifically with these two lines that are almost on top of each other. During this correlation process, it was concluded that the input losses previously suspected were also a large contributor to the low performance. Well, this is then given some of the considerations of the project. There were limited time and budget constraints. Specifically, with the time, there was a specific season in which we were to test that the lecturer said was ideal, so we were going for that and trying to get the construction finished by that time. And as for the budget, just the 8 lenses alone already went over the budget, so all the rest we had to sponsor from our own pocket. And this then led to the mathematical correlations that do not fit the system perfectly, as well as to the flaws in the flex design that severely hamper its performance, and this specifically in the thermal contact resistance from the conduction core subcomponents and the input losses from things like dirty lenses, dirty mirrors, the misalignments in the structure, and an unstable frame. On the topic of cost considerations, Currently, due to the amount of flaws and unknowns, it is considered that the cost analysis versus performance is not yet a fair comparison. And this is because it would be comparing the input versus a sub-optimum output, or in other words, the output could still be improved. And as such, it is concluded that further research is still required. Some system observations that were made. It was very easy to work with this system, specifically with focusing the Fresnel lenses and collectively aligning them with the sun. The Fresnel lenses are also resilient and can continue to operate despite physical damage. For instance, at one stage I accidentally cut one of the lenses during the construction, and we could just continue working with it. But the cleaning of a Fresnel lens is something that needs to be considered specifically for future research. A specific phenomenon was also observed called solar return, where in a large-scale system, it can be dangerous if there isn't a receiver in the center. This is because the solar radiation would go to the reflector plate through the Fresnel lens, but now nothing is receiving it, so it would continue to dissipate to the other side, refocus back there through the reflector and back out into the unknown. And I experienced this when I was on the receiving end. So, yeah, and this ties into the necessity to cover the mirrors or lenses when the system is not operated, or in other words, with the safety that is considered very important, as a dish can even damage itself in idle, or worst case scenarios when you burn yourself, such as I did during the experiments. So, on the other hand, the correlated theoretical model could then also be used to predict the approximate system performance for different variables. For instance, assuming this flex D1 model were then fixed of all its flaws and the concentrating system scaled up, but still using the same receiver size as shown with this figure, the following results were obtained, where it could be seen that the initial target temperatures could be reached very quickly. Or in other words, this presents us with the possibility of quickly heating up small quantities. In conjunction with this, the FFD layout presents the possibility of fast target material replacement. This is because the receiver is now conveniently placed near the main dish structure, while also providing convenient gaps where feeder or retriever subsystems can be implemented. This then leads to the various possibilities of useful work that can be harnessed, from large-scale HVAC, power generation, or industrial purposes, to even small scale such as domestic or even camping size kits that my mentor yesterday actually mentioned. This then leads to the conclusion, where it was initially asked, is such a system plausible? To which it currently is believed, yes, it is plausible. It achieves the goal, which was to provide a more durable, concentrating mechanism requiring less refurbishment. But there were lots of hurdles and flaws experienced in this system. But if these are overcome, it is predicted to provide good potential. But also with this, it provides other possibilities, such as the foldability and the enclosure and protection of the system components that can possibly be done, the unique dish layout, which possibly allows for easy access or feeding to the receiver, and subsequently leading to the useful work capabilities that can be done. As such, it is concluded that further research is both required and encouraged, and specifically for a Flex D2 model to be constructed, fixing upon all the previous flaws. And with this is then given the following recommendations: to develop methods to clean the lenses and mirrors effectively, to construct a solid conduction core receiver, and this is to remove the thermal contact resistance in it, to stabilize the system, such as using a stronger structure, to improve the theoretical model by creating mathematical correlations that are developed for the FFD receiver, and then to do a more in-depth feasibility study on the improved system. This is to provide a more competitive comparison between the output and the input that we had to give to get that output. Also, to investigate the Fresnel lens manufacturing more in depth. This to provide a better, more optimized system design, while also providing for cost-effective sourcing. And finally, to investigate the FFD system possibilities, such as for feedability, foldability, and useful work capabilities. And with that, I conclude my presentation. Thank you for your time.